Hello, welcome to the heat transfer lecture. Today's topic is extended surfaces. Extended surface heat transfer is an important engineering application. These extended surfaces are also called as fins, which are used to increase the heat transfer rate by increasing the heat transfer area. So we'll derive for the governing equation. So in this derivation, some assumptions are required. That is, the fin material is homogeneous and isentropic. Hence, the thermal conductivity of the fin material is uniform. The temperature at any cross section of the fin is uniform. That is, T is the function of X only. In other words, the heat conduction is one dimensional. The heat transfer coefficient is uniform over the entire surface. There is no heat generation. Contact thermal resistance and radiations are negligible. The heat conduction is steady state. Now consider a surface attached to a parent surface as shown in figure. Take small slice at given distance x need not be circular as shown. So with respect to x, the heat conducted is qx. With respect to dx, the heat conducted is qx plus dx, and with respect to dx, the convection is dq convection. Now we'll apply the energy balance. That is, heat conducted at x is equal to heat conducted at x plus dx plus heat convected between x and x plus dx, or qx is equal to qx plus dx plus dq convection. By using Fourier law, Newton's law, and ignoring higher order terms in the Taylor expansion series, that is, heat conducted at x, qx is equal to minus kac into dt by dx, where k is the conductivity, AC is the cross sectional area, and dt by dx is the temperature profile. Heat conducted at x plus dx, that is qx plus dx, is equal to qx plus d by dx into qx of dx. Heat convected from length dx, dq convection is equal to h into das into t minus t infinity, where h is the heat transfer coefficient, as is the surface area, t is the temperature with dx, and t infinity is the atmospheric temperature. So we'll replace this area in terms of perimeter, and therefore dq convection is equal to h into p into dx into t minus t infinity, and therefore the energy equation balance is minus kac into dt by dx is equal to minus kac into dt by dx plus d by dx of minus kac into dt by dx into dx plus h into p into dx into t minus t infinity. Here minus kac into dt by dx will cancel, and the equation is d by dx of minus kac into dt by dx into dx plus h into p into dx into t minus t infinity is equal to 0. Again dx will cancel, and the equation is d by dx of minus kac into dt by dx plus h into p into t minus t infinity is equal to 0. Now we'll assume that the cross sectional area is constant and the thermal conductivity is also constant, and therefore the equation is d2t by dx square is equal to hp upon kac into t minus t infinity. So this is the non-homogeneous second order differential equation. So to convert this equation as a homogeneous, we will use the following transformation. That is, theta is equal to t minus t infinity. Therefore d2 theta upon dx square is equal to d2t upon dx square, and therefore the equation is, that is the final equation, d2 theta upon dx square is equal to m square into theta, where m is the under root of hp upon kac. The constant m has the physical significance, that is, if we multiply by L, that is the length of fin, then m into L is equal to HPL upon KAC divided by L, which is nothing but the ratio of surface conductance to the internal conductance. So this equation is called as a general governing equation. And the solution of this equation is that theta is equal to t minus t infinity is equal to c1 e raised to power mx plus c2 e raised to power minus mx. Now we can use this equation to find out the temperature distributions and the heat transfer for different cases, that is the insulated fin, infinite long fin, and heat loss from the fin, which is also called as a exact solution.